Okay, this is the central limit theorem. Let's dive in. All right, let's give you a quick definition of the central limit theorem. Turns out it's really important. It's kind of the foundation of a lot of statistics. It says that the sample means will be normally distributed regardless of the shape of the starting distribution. A couple of things going on there, two big ideas. One, the sample mean, any sample that you pull, its average can be will be close to whatever the population mean is. But it's possible it could be unusually small or unusually large, surely by chance. It has that bell-shaped curve, essentially. And two, is that this bell-shaped curve will appear regardless of how likely it is that an observation will have any particular value. The best way to really understand the central limit theorem is with an illustration. Okay, this is an Excel document I made. You can see in the upper right-hand corner, well, upper left-hand corner, we'll start with A1, and I've told it to select a random number, multiply that number by 10, because the basic random number is between 0 and 1. And then I told it to make it an integer. So that means I told Excel to get anywhere between 0 and 9 integers only. So I got zeros, I got ones, I got 6s and 5s and 8s. Any one of these numbers has an equal chance of pulling off. I should have 10% of everything. And then I told it of this sample of 5, this is a simulated sample of 5, I told it to take its average, A1 to E1. Sample of 5, here's the average for that sample. Sample of 5, here's the average of that sample. And I told it to do this 1,000 times. So I have 1,000 sample averages. And if I were to take a sample, I could get any one of these. I could get something that is close to the middle, as we would expect, about 4.5. I could get something that is kind of small, like 2.4 here. I could get something that, there's one even smaller, is 1.8. Or I could get something that's unusually large, like 6.2, just by random chance. So what I did is I told Excel to put all these different averages into a histogram. Here's that histogram. And you'll note that histogram with a very small number of observations here on the extremes, a lot of them in the middle, it has that familiar bell-shaped curve. And if I were to press F9, it will choose new random numbers, all 5,000 of them, and I still get a bell-shaped curve over and over and over and over again. This forms the basis of hypothesis testing. When you get a sample and you look at its average, and you see that it's really big or it's really small, you have two different things going on. It can either be big or small because something is weird now, something has changed, and you just found evidence that something has changed. Or it could be big and small just because you happen to get a result that's big or small. But because this forms a normal distribution, you can use the empirical rule to figure out how likely is it that you got something large or small just by random chance. And what's particularly useful about the central limit theorem is that, as noted, this is true regardless of the distribution from the population. Here, this was a uniform distribution. Right? Every element had an equal chance of showing up, a 10% chance. But we still got a normal distribution when we looked at the averages. Another thing that comes up is that you discover how important sample size is. If you have a larger sample, then it's less likely to be unusual simply by random chance. It's one thing to get a bunch of 8s and 9s in a sample size of 5. It's quite unusual to get 8s and 9s in a sample size of, say, 10 or 20. And I can show you this with another version of this I did. Same story, but now the sample size is 20. Still took the average. And here's my distribution. Again, it's a normal distribution. It's more peaked, right? But you still see that tail, and it comes up in the middle. It's still tail. It's still symmetric. Kind of looks like it's like flipping me off. But if we take F9 and go over and over again, we still see it has a normal distribution. Right? But it's really unlikely that you got a bunch of 8s and 9s. It's really unlikely your average will be over here. It's really unlikely your average will be over here. It's less likely to be here, and most of it now is concentrated up here. Sample size is crucial. Sample size is the biggest thing. So from the central limit theorem, we get a key lesson. In statistics, it isn't about proof. You can never really prove stuff with statistics, because when any sample you get and you see that it's unusual, you can't claim that this is proof, because it could be unusual just by random chance. Proof is too strong of a word. So instead, in statistics, we use phrases like providing evidence. This suggests, this seems that, it appears, this demonstrates. Prove is too strong of a word. Thanks for watching.